Introduction to sequences and series, this is just introduction, so we'll see the patterns around us or sequence around us, and the formal and informal definition of sequences, and finally we'll see the different forms or types of sequences, and we'll just roughly see the definition of series. Okay, let's start with definition. I mean real life application. Look at the informal definition of sequence. This is informal definition of sequence. A sequence is an ordered pair. Okay, as you can see, it is an ordered pair list of numbers or objects. Okay, so we'll start with object separated by a commas in a sequential fashion. So let's start with object. Okay, you can see, pause the video, think all the sequence or the patterns around you. Okay, think of those patterns or shapes or objects in different patterns or in different shapes. Okay, sequences are everywhere around us. Okay, look at the object around you, pause and think the sequence or the pattern of anything in front of you, or think of those patterned objects. Okay, let's move on. Look at this one. This is our cultural baskets, tales of threads. As you can see, we have different patterns here. Okay, this is a traditional basket, as you can see. Okay, you can see here, you can see similarities. Okay, if you fold, for example, if you fold this one and if you fold this one exactly, the upper one is exactly reflection of the bottom one. Okay, so this is of course kind of Fibonacci sequence. We'll discuss this in future. This is so amazing. This is so cool, so amazing. And we can also this in nature. I mean, we can see this in flowers. Okay, look at this one. We can have this pattern. Okay, this Fibonacci patterns in flowers too. Look at this one. Okay, look at this one, the same pattern. So this is handmade. It's so amazing. The perfection is so amazing. Okay, look at this one. This is again a cultural clauses. Okay, cultural clauses, especially this is from Dorje tribe. Okay, so if you just draw a line here, line here, let it be line of reflection. Okay, the top one is exact reflection, exact copy of the bottom one. Okay, if you draw this one, look at the even look at this one. You have here 1 2 here, and you have 1 2 here. You have 1 2 2 4 6 8 here, 2 4 6 8 here. It's exact copy of what's in the bottom. This is so amazing. Just read, just handmade. Wow. Okay, let's see another patterns. You can see this all in any traditional clauses. Okay, so let's see this one. Let's see this is in real life. I mean real life application of sequence. This is of course, as you can see, seed, germination and sprout, seedling and plant. Of course, you know there is a nature that governs all of us. Okay, you can't skip from seed to directly to plant. There has to be a sequence. There has to be patterns. The same is true for animals too. Let's see this. We have here the bugs. Okay, so of course we start with adult. That one also should be kind of cyclic. So egg, we have larva and pupa and adult. This is so naturally this is happening. It's just a sequence. It is a pattern. Okay, look at this one. This is a sequence is found also in chemistry. This is distillation. Okay, to make arake, so we're using distillation, right? This is traditional, of course. Now we are modern, but the point is there is a sequence to make arake or any touch or tala. There has to be sequence. Okay, so we have also have here. Look at this one. This is origin. Okay, current. This is kind of again Fibonacci sequence. Okay, you'll see this pattern in oceans. This is so amazing. So let's see another sequence. Look, we have people's lines here. This is a sequence. Okay, we all look at this one. Nobody's coming here because there is a sequence. Okay, whoever comes has to be at the last. Okay, so naturally we are governed by the sequence. And this is also happened I think this election. This also happen in case of planet or the universe. Okay, look at the planet. Okay, every planet around or revolve around the Earth, Sun with fixed ways, that is orbits. Okay, it's impossible for Earth to skip and come to here. Okay, so we are governed by the rule. We are governed by some way of, like in this case, gravity. Okay, so this is what it looks like in nature. Okay, so now let's see the formal definition of a sequence. So a sequence is a function. It is a function. Okay, therefore, as any function has a domain and range, sequence also has a domain. Okay, whose domain, okay, let's continue, whose domain, okay, let's see the domain in two ways. Okay, let's see the domain in two ways. Whose domain is positive integer, if the set is, if the sequence is infinite sequence. Okay, if it is infinite sequence, so the domain will be positive integer, which means you have 1 2 3 up to ends again, it's just continuous. Okay, so if the domain, I mean if the sequence is finite, we're going to use only the ends, or the first ends. Okay, natural number will be the domain. So this is true if our sequence is just finite or fixed, or we can have the end. So in this case, for example, we can say n 1 2 3 up to just n. Okay, it doesn't continue after n, so the first ends natural will be the domain. Okay, so let's see, let's represent the function. Okay, how do we represent a sequence? Representing. Okay, let's represent r, or let's denote, okay, a sequence. Okay, sequence usually or often represented by letters. Okay, where we often use, let me write down. Often represented by letters. Okay, usually small letters with subscript. Okay, in the form of let it be like, let's use different, like a n. Okay, maybe we can use bn, we can use cn, and so on. So in this case, the subscript, we can read this as maybe a sub n. Okay, maybe you can read like this, or b sub n. So what does this subscript tell us? Okay, the subscript just let be in this case, n refers to the ends element of the sequence. Okay, it refers to the ends element of the sequence. Okay, so even it tells us the position. Like in this case, we can say like a1, a sub 2, a sub 3, a sub 4, and so on. So the position of the element in the sequence is its rank or index. Okay, this position is, we can say, its rank or its index. Okay, now let's compare the element. Let's compare the element of a sequence with respect to the set. I'm not saying the sequence is the same as the set. No, let's compare only with respect to the element. Okay, let's have here set, let's have here sequence. okay, sequence. Okay, so both of them, okay, both of them has element, okay, element, which is member of the set or member of the sequence is called element. In this case also we have element, but there is a big difference. Element, okay, we have element. So for example, indicate the number of element is called the length of the sequence. Okay, the length of the element is called the length of the sequence, but in this case just only the element. Okay, the other one is the set of, in the set the elements are not depend on order. Okay, order doesn't matter here. Okay, we can say order okay doesn't matter. Okay, order doesn't matter. Okay, but in this case it does. Okay, this is definitely order dependent. Order dependent. Okay, it's just order dependent. How is that though? Which means maybe we can say let's see some example. For example, we may have a sub n is a sequence which is represented by -1 to the power of n. So if n is even, okay, if n is the even, let's be like this. If n is even, okay, let's, if 1, n is 1, so we have -1, n is 2, we have 1, n is again 3, we have -1, 1, and so on and so on. So as you can see, you have to list all of them. You have to list all of them. But in the case of element, you don't have to list all of them. The only element we have here is -1 and 1. Done. So we may represent this as -1 and 1. Okay. So for the sake of just simplicity, we can write negative first and positive next. But it doesn't matter in which order you wrote. But in case of the sequence, it is highly order dependent. Okay. The other one is the same element can appear here. In this case, the same element can appear multiple times. Look at this one. So here you have maybe you can write this one as -1, -1, 1, 1, but you have 1 here, 1 here, you have -1, -1 here. So the same element can appear multiple times here, okay, in different positions. Sequence. So these are the main difference between sequence and a set. But still keep in mind that sequence is a function, but set is not a function. Okay, now let's see the different forms or types of sequence. When we come to the forms of a sequence is, let's see the sequence in 4 different ways, okay? In 4 different ways. The first one is arithmetic sequence. So in arithmetic sequence is a sequence with a difference between 2 consecutive term constant, which means in order to find the next number, you have to add or subtract some constant numbers. Okay, for example, look at this one, 1, 2, 3, 4, 5. This is just a natural number. So to find the next number, you have to add 1. Okay, the difference is 1. 1 plus 2 is 3, 3 plus 1 is 4, and so on and so on. So this is arithmetic sequence. The next one is geometric progression or geometric sequence. We can also say progression. It is a sequence with ratio between 2 consecutive terms constant, which means in this case, to find the next term, is either you have to multiply or divide with some constant. So, for example, you have here 2, 4, 8, and 16. So the next 2, I think it's just increasing by multiple of 2. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. It's just a constant, is a multiple of a constant of 2. Okay, so let's see, we may have, this is just single example. The sequence could also be decreasing. The same is true here. The other one is recurrence, which is not a recurrence progression, is a sequence once 1 or more initial term are given. This is the difference. 1 or more initial terms will be given, and then each term after that, okay, each further term of the sequence defined as a function of the preceding term. Okay, the next term depend on the previous term. Okay, so this is not geometric progression. Recurrence progression is not arithmetic progression. This is just different. Let's see, the best example for recurrence progression is Fibonacci number. Okay, of course you will see a video, or I will do a video and you can watch. So Fibonacci number is a number, for example, 1 and 1, 0, 1, 1 is given. So to find the next number, for example, if you have 0 here, 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on and so on and so on. So this is the most famous recurrence progressions. Okay, we'll see this. This is amazing. Okay, so the other one is neither arithmetic or geometric or even not a recurrence. Okay, so we can, let's see one example here. For example, prime number. Okay, say the prime number is an example. It's not, it is not arithmetic, because look at this one. Even though the difference here is 2, here is 2, but in this case the difference is 1. It's not geometric because none of them is a multiple of the other. It's not recurrence. As you can see, one is not dependent on the other. It varies. So this is not. This is something. I can say we also have another progressions, another sequence which is not listed in here. Just to focus on some of them. Okay, and on the next video we'll see all basics of arithmetic progression and geometric progression, and then I will do a separate video for Fibonacci sequence in real life. Okay, the other one is series. Okay, I'm gonna just stop here. Series is just the sum of the sequence. When we add up all the sequence, it gives us a series. Okay, so we'll see more on next videos for each